Hello there, I'm Phone Yuan, presenting our ICCV work, Humans as Checkerboards hack, Calibrating Camera Motion Scale for World Coordinate Human Mesh Recovery. In Human Mesh Recovery or HMR, the aim is, given some input video like what you see on the left here, we want to estimate the 3D meshes of the entire human body. Now usually the 3D meshes that we recover are local, in the sense that the 3D mesh sits only in the camera coordinate space. But what we would like to do is recover these meshes in world coordinates. This is what we refer to as global HMR. The problem, of course, is that what we see in the video here is an entanglement of both the human motion and the camera motion. Like both human move in the world and camera move in the world, they together produce the observed video. And because the two are entangled, so many setups, I am showing two examples here, in the red and purple insets, will give you the same observations or videos. So how can we disentangle the two motion components? Well, one strategy is through a purely data-driven approach. Simply learn and approximate the global motion from the local motion. These are local to global strategies that basically try to learn what the global motion should be based on the local observations of the motion and velocities, from which we can predict the overall global trajectory of the person, and then compose with the local motions to get the global motion. But as you can imagine, such approaches may fail under ambiguous observations. A good example is here where the man is skateboarding. His local motion, because his feet are stationary on the skateboard, suggests he only sways back and forth, and that's what you have in a local to global approach. Here, this example is from the WAM paper from CVPR 24. Even though, as we can observe in the video, the man should be traversing forwards on his skateboard in world coordinate. More ideal, of course, is if we can fully decompose the two components, basically the camera motion itself. And this is a commonly studied problem in 3D vision and robotics, essentially solving the monocular slam problem. This is all fine and good, and we have some state-of-the-art slam methods now that work quite well, such as droid slam and DPVO. But because we are dealing with monocular slam, we have one degree of freedom, which is scale factor for camera motion, that cannot be resolved. This is why in standard tracking setups there is a camera calibration phase, for instance with the checkerboard patterns where we can match a known distance. Basically we know the real-world size of the checks against the observation in the camera to estimate this scale. But because we are dealing with video sequences taken in the wild, they aren't calibrated against anything. So one strategy we can take is to directly solve for it with optimization. We optimize against the projected 2D key points against detected 2D key points in the scene, and factor into the reprojection not only the body itself, but also the camera trajectories. Essentially, we set up this huge optimization function with a lot of terms and simply solve. But of course, this optimization, because of the nature of the problem, is unconstrained. Solving this optimization is costly. It takes about 15 seconds per frame. Thus, one way to get rid of the heavy optimization is trying to get metric scale by off-the-shelf depth predictors like Zoe depth. The idea is simple. You feed the video frame into a pre-trained depth model and it gives you metric depth for the scene, which you can then use to scale your reconstruction automatically, no optimization needed. But the catch is they rely on the background. If the background lacks good depth cues or the prediction isn't reliable, the scale value becomes noisy or wrong. So while it's easy and optimization-free, it's also fragile when the scene context is weak. That's why we need something more robust and human-centric, which brings us to using foreground humans as checkerboards in this paper. Here's our proposed pipeline. First, we run a masked droid slam on background to recover camera motion and scene point cloud, but the scale is unknown. In parallel, we apply HMR to the foreground to predict the 3D human pose and estimate the metric depth of contact joints, like the feet touching the ground. We then compare the slam's relative depth for those contact points with the HMR's absolute depth to compute a scale factor. This lets us convert the slam trajectory from relative to metric scale, without any heavy optimization. Finally, with this calibrated scale, we fuse slam and HMR motions to get accurate global human motion and camera pose in real-world coordinates. This approach is simple yet powerful, no optimization needed, and highly accurate. Here, how we compute scale in a frame-by-frame way. For each frame, we take the contact joint, the lowest joint along the camera Y direction, basically gravity, get its absolute depth from the HMR output, for example the foot joint here, and then take the relative depth of reference point from slam point cloud, for example the ground point which should be in contact with human foot. Then we compute a simple ratio SF. That gives us the frame level scale factor. To make it robust, we take the median of all these frame-wise scale factors across the video sequence. That's our final scale S. Then we can correctly scale the slam output to fit the human depth. Sometimes the contact joint is not visible in the camera view, like here in the upper left egocentric video. In those cases, we fall back on a ground plane fitting approach. Here, how it works, we assume that the person's feet locate on the ground. Then the plane normal factor is fitted by the feet sequence across the video, and the plane offset is determined by the lowest segment of point cloud. With the plane, we can determine the contact depth from HMR and the relative scene depth from SLAM as in the normal cases, just as if the foot was visible. For example, the reference point from point cloud is the intersection point of the plane and the ray from camera to contact joint. That way, we makes the scale calibration applicable in challenge and ego-centric scenarios. As for the result, first the trajectory plots show that before scale correction green traj, SLAM's paths are off-scale, but with HAC blue, they align much closer to ground truth gray. Second, HAC is incredibly fast. In the runtime bar chart, HAC is many times faster than optimization-based methods like SLA-HMR. And HAC produces cleaner disentanglement than WAM, and more accurate scale calibration than TRAM's background-based methods. Now, how well does HAC generalize? These examples show it works even in complex scenes like staircases and unusual poses. In a nutshell, HAC is more accurate, significantly faster, and more reliable across diverse setups. Alright, so to wrap up, let me highlight the key takeaways. First is HMR contains priors that we can leverage. For example, the human mesh can give metric cues for scale calibration and can also serve as landmarks in bundle adjustment. Second, sometimes it's all about decoupling motion properly. In world coordinates, we need to separate camera motion from human motion. And accurate scale gives better camera motion, which lead to better disentanglement and better global human motion. Thank you all for listening. I'd be happy to take any questions.